Hello everyone, welcome to my presentation. My paper is called HOIGaze, Gaze Estimation During Hand-Object Interactions in Extended Reality, Exploring Eye-Hand-Hand Coordination. I am the presentation author, Zhiming Hu. Here is the link to our paper, and we also provide the QR code to the paper details. Here is the outline of my presentation. We are going to introduce the research background, related work, method, results, discussion, and also the conclusion. Well, let's start with the background. Human eye gaze is important for many XR applications, including the gaze contingent rendering, which use your eye gaze to determine the region that we need to render with high quality. And also, human eye gaze is also important for many gaze-based interactions, which use your eye gaze direction and durations to interact with 3D objects in XR environments. Human eye gaze can also be applied to many applications like the activity recognition, which uses your eye gaze directions to recognize your activity. Now, let's talk about our motivation. We observe that during daily hand-object interactions, we find that your eye gaze are coordinated with your head orientations and also your hand gestures. So, based on this observation, we would like to estimate your eye gaze during HOIGaze using the eye-hand-hand coordination. Let's talk about some related work. The eye-hand-hand coordination is a hot topic in the area of XR. For example, people have explored the eye-hand coordination during gaze shift in XR, and also the coordination between your eyes and your hand trajectories during object manipulation in XR. Prior works, they only explore the correlation between eye gaze and hand trajectories. In contrast, in this work, we would like to focus on the coordination of the eye gaze and the hand gestures. And in addition, we would also like to estimate the eye gaze using this eye-hand-hand coordination. Let's go to the method. Before we introduce our method, we would like to introduce a new concept called attended hand, which means which refers to the hand that is close to the eye gaze in terms of angular distance. For example, in this situation, the man's eye gaze is first focused on his right hand, and then is focused on the left hand. So the right hand is the attended hand, and then the left hand is the attended hand. Our method is a hierarchical framework in which we recognize the attended hand, and then based on the attended hand, we extract the objects that are close to the attended hand, and then we use those information to estimate your eye gaze. So specifically, we use the 1D convolutional neural network, spatial temporal graph convolutional neural network to extract features from your head orientations, your left and right hand gestures. We use those. We combine those features to recognize the attended hand. And then after we recognize the attended hand, we extract the objects that are close to this hand, and then we extract the features from the attended hand and those objects. And then we use cross-model transformers to fuse the features from the head orientations and the attended hand and objects. Finally, we combine those features to use a 1D CNN to estimate the human eye gaze. Well, we also introduce a new eye-hand coordination loss that increases the weight of the loss assigned to the eye-hand coordinated samples. The insight is that we observe that the eye-hand coordinated samples, they are more important than the samples with little eye-hand correlation. So we want to increase the the width of the coordinated samples to increase the performance of the gaze estimation method. Well, let's talk about some results. We estimate our method on two public datasets, namely the whole 3D dataset and the ADT dataset. We perform cross-user and cross-scene evaluations. Cross-user means that we train our method on some users and test it on other users. Cross-scene means that we train our method on some scenes and test it on other scenes. From the results on this table, we could say that our method outperforms the prior methods for both the cross-user evaluation and also the cross-scene evaluation, and also for both the whole 3D and the ADT datasets. Here we show some visualization results of our estimation. Well, here the green lines is the ground truth. The red lines are our predictions, and the blue lines are the state of art. We could say that at different situations, different hand-object interactions, whether it's the single object interaction or the two interactions with two objects, our predictions is more close to the ground truth than the state-of-the-art method. We also have the video that shows some dynamic visualization results. We could say that at different interactions, at different objects, our predictions is more close to the ground truth than the baseline method. We have also performed an ablation study, which we remove the attended hand, which means that we don't do the attended hand recognition. We directly use both the left hand and the right hand as input. We remove the cross-motor transformers. We remove the eye-head coordination loss. The results validate that each component is important to our method. Well, in addition, we also evaluate our method on the downstream task of gaze-based activity recognition. In this evaluation, we use different methods to estimate the human eye gaze, and then we use the estimated eye gaze to do the gaze-based activity recognition. The higher the recognition accuracies, the better the gaze quality. We find that our method also achieves higher recognition accuracies than the baseline methods. Well, we also identify some limitations of our method. First, our evaluation datasets only contain interactions with real physical objects. Secondly, we ignore the influence of the imagery or textual features on eye gaze. So in the future, we would like to evaluate our method on interactions with both the real and virtual objects. In addition, we would also like to integrate the imagery or textual features into our method to further boost its performance. Well, let's come to the conclusion. So the main contributions of our work are listed below. We propose a novel hierarchical framework, hierarchical framework that contains an attended hand recognizer and an eye gaze estimator. We also provide a new gaze estimator that combines the GCM and the cross-motor transformers. We also propose a novel eye-head coordination loss. In addition, we conduct extensive experiments on two public datasets, namely the whole 3D dataset and the ADT dataset, and we demonstrate the effectiveness of our method. Finally, we also perform experiments on the application of gaze-based activity recognition and shows that our method achieves higher recognition accuracies than other methods. And in these results, validate the usefulness of our method in downstream tasks. Here is the references used in the presentation. That's all for my presentation. Thank you very much.